in this lesson, we're going to be talking about the ideal gas law. And this one's different than the other laws because in this one, all conditions are constant. There's no changing conditions. It's not like the pressure started out at 1 atmosphere and then over time it changed to 2 atmospheres. This is where the conditions are staying constant. That's why it's ideal situations. It would be ideal if the pressure never changed. It would be ideal if the temperature never changed. But in reality, pressure is constantly changing, temperature's changing. In the morning, it's one temperature. In the afternoon, it's a different temperature. And these things affect gases. So this law is showing what happens if things don't change. So that's why it's the ideal gas law. And the equation for the ideal gas law is PV equals nRT. P stands for pressure, V is volume, T is temperature, just like it was in the other equations. We have a new letter here, the letter N, the lowercase n, and that stands for the number of moles. If you don't have moles and you have grams, then you're going to have to convert, which we learned how to do back in chapter 11 and we used in chapter 12. The capital letter R is this thing called the ideal gas constant, and it's a number that's not going to change. And the R value depends on the unit for pressure. So it all depends on if the pressure is measured in atmospheres, kilopascals, torrs, millimeters of mercury, which value you're going to use. So what is this R value? Well, the R value is different depending on the pressure unit. So you can see here, volume has to be in liters, cannot be milliliters. Temperature has to be in Kelvin, just like it was in Charles' law and Guy-Lussac's law and the combined gas law. N has to be moles, so if it's measured in grams, you have to convert it to moles. But pressure is the only one that you can use a different one. You can use atmospheres, kilopascals, millimeters of mercury, and remember, a millimeter of mercury and a torr are the same thing. They're both 760. So this is the only one where you can use a different unit. But depending on what the pressure is, you have a different R value for each one. So for example, if the pressure is measured in atmospheres, the R that you're going to use is 0.0821. If the pressure is measured in kilopascals, the R that you're going to use in your problem is 8.314. If your pressure is measured in either millimeters of mercury or torrs, the R that you're going to use is 62.4. Now it's got a crazy unit for the R value. It's the volume unit times the pressure unit, and notice in each one the pressure unit is different, and this one here can be millimeters mercury or torrs. You divide those two by the moles and the kelvins. Okay, so make sure you learn that unit because it's a big one that you're going to be using in your problems. Okay, so for here, our first problem, we have if the pressure exerted by a gas at 25 degrees Celsius in a volume of 0.044 liters is 3.81 atmospheres, how many moles of gas are present? So we have a pressure, it's 3.81 atmospheres. It's not changing. That's why it's an ideal situation. Nowhere in this problem does it say it's changing. The volume is 0.044 liters. The number of moles, well, we don't know. That's what we're looking for. The R value for this problem, since the pressure is measured in atmospheres, look at the chart. The chart says that the R value has to be 0.0821 liters times of atmosphere divided by a mole times a Kelvin. And then the temperature is 25 degrees Celsius, which will change to Kelvin, and that's 298 Kelvin. our equation is PV equals nRT. So our pressure, we're going to move this out of the way. Our pressure is 3.8 atmospheres. The volume, 0.044 liters. That is equal to the number of moles, which we don't know. The R, 0.0821 liters times an atmosphere over a mole times a Kelvin. And then the temperature is 298. Again, just like all the other ones, make sure you're using the Kelvin temperature and not the Celsius temperature there. No changing conditions. We go ahead and we solve for our number of moles that we have, and we get 0.0069 moles of gas in this particular problem. We only need 2 sig figs in our final answer. Okay, what about this one here? It says determine the Celsius temperature, so we're going to have to convert back to Celsius, of 2.49 moles of gas contained in a 1 liter vessel at a pressure of 143 kilopascals. So our pressure, 143 kilopascals. The volume is 1 liter. The N, the number of moles, is 2.49 moles. If that was in grams, we'd have to convert it to moles, but we're okay. The R value for this particular problem, since it's in kilopascals, the pressure, you have to use the R value for kilopascals, which is 8.314. And the unit, oops, it should be liters times kilopascals, but that's okay. Mole times a Kelvin. And then the temperature is what we don't know. That's what we're looking for. So the ideal gas law, PV equals nRT. And we go ahead and we plug our stuff in here. So 143 kilopascals. Our volume is 1 liter. The moles, 2.49. The R, 8.314. And the temperature is the thing that we're looking for in this particular problem. So when we go ahead and we solve for our temperature, our answer is going to be in Kelvin. So 143 times 1 divided by 2.49 divided by 8.314. So you get X is 6 point, how many sig figs are we going to need here? We're going to need 3, 6.91 Kelvin. We want the temperature in degrees Celsius because that's what it says in the problem. So I'm going to have to take 6.91 minus 273 to get back to our Celsius temperature, and it is negative 266 degrees Celsius. And we have one more problem we're going to practice. This one says calculate the volume that a 0.323 mole sample of a gas will occupy at 265 Kelvin and a pressure of 0.9 atmospheres. So the pressure, 0.9 atmospheres. The volume is X. That's what it's asking us to solve for. The number of moles is 0.323 moles. The R value, since it's in atmospheres, we're going to have to use 0.0821. Remember, these are coming from the chart on that previous slide. If you're wondering where that number is coming from, because it's not in the problem. And temperature is already in kelvins, 265 Kelvin. So we'll plug it in, 0.9 atmospheres. The volume is our X, our moles. All of these problems, they gave us the information in moles, but on your homework, you're going to have some where it's in grams and you're going to have to convert it into moles. So be careful with those. R value, and then the temperature, 265. Go ahead and plug that in. Each of these numbers have 3 sig figs, so our value for X, which is volume, is going to have 3 sig figs, and it's 7.81 liters as our answer.